Welcome to lecture 19. So, today we will talk about pragmatics. So, let's start with a typical runtime structure. So, uh, so implicit in the assumptions of this is that we are considering some form of block structured or statically scoped languages. In most of these languages, there is a typical runtime environment consists of these entities. Firstly, there is this runtime stack, which actually has data which is created and maintained at runtime, and there is a current environment pointer usually stored in some register. So, this is the base address of the current block that has been entered during execution time at execution time. So, this is a purely runtime structure, right. And what happens is, so you can consider this to be all the memory that you have available for the execution of the program, and that memory is divided into two portions. One is what is known as the stack, and the other is what is known as the heap, right. So, the heap, let's make it very clear that the heap has got nothing to do with the heap data structure that you may have learnt in some data structure course. Here a heap just means a heap of data, that is it. I mean, it is literally a heap. I mean, it is like a junkyard. I mean, there is nothing else to it. Okay. So, the heap typically, so a normal sort of structure is that if given a certain amount of memory that you have available for your program, for the execution of a program, you divide it up into some, you make some arbitrary division, and which is not entirely which is such that the heap starts from here and grows maybe down, the stack starts from here and grows up, right. So, essentially what if you have to partition a memory for optimal use, what you can do is what you do is you try to optimize depending upon you before compiling the program, you really have no idea how much of the allocation can be done at compile time, how much of the allocation has to be done at runtime. Okay. So, if the program has some runtime data structures like the typical Pascal new and dispose, then you really have absolutely no idea how much space you might have to allocate dynamically at runtime for the program. And instead of dividing it up really arbitrarily, this division between the heap and the stack is really an artificial division. What usually happens is that you do not want to fix the stack size or the heap size. What you want to fix is only the total memory size, and then so you let the stack grow during execution from one end, and you let the heap grow over another end. So, what happens, a typical when you are out of memory, a typical error message that you get is that stack overruns heap. Okay. So, if you have a large amount of data such that at any point during the execution of a program, if the amount of data is such that it just cannot be accommodated, either it could be just statically allocated data which is going to be allocated on the stack, or dynamically created data, huge amounts of lists, pointers, trees and so on, all those dynamically allocated data, there is just no more memory to allocate more data. So, you will get a typical, this stack overruns heap means that there is only a fixed amount of total memory, and if your program is such that you have declared all the data that you require there are no pointers, then the entire space could be used as a runtime stack. If your program is such that it has very little actual statically allocated data, but a large amount of dynamically created data, and this you are creating lists and trees and destroying them and creating new lists and trees and very little static data, then what it means is that your heap will grow downwards much closer. You would require a smaller stack size and a larger heap size, and that is often not determinable at compile time. So you just let them grow one towards the other till you exhausted the memory and then you exit, right. Otherwise, if there is no if you do not run out of memory, of course then things are fine. So the heap is something that we will talk about later, but it's important to know that such a thing exists. It's just necessary to know that all the dynamically created data is stored in the heap. So a typical Pascal new or dispose means that you're allocating data whenever there is a new allocation to a pointer data, that means that data is going to be allocated in the heap, right. And of course the heap requires, I mean there are problems like if there is a large amount of allocation and deallocation going on through, let us say, new and dispose, then the heap might get totally fragmented, okay. And there is absolutely no way of accessing the heap because you do not know where the data in the heap is. When you create a new data, you just have to take it from somewhere, you just some allocation from the next available data is. So even though you might contiguously allocate pointers initially, as you keep disposing of old structures and creating new structures, what can happen is that your heap space can get thoroughly fragmented, okay. So but all accesses to the heap will have to be from the stack, because the only fixed addresses that you have come from the stack. So the starting point of any list or the starting point of any tree would be some location, something that can have a fixed location. Essentially, in order to for dynamic data structures, what you require is some way of statically allocating some place where you can store an address, right. And addresses are of fixed size, so you can statically allocate one address or a finite number of addresses that are pre-declared in the program, but that's all you can really allocate on the stack. So all accesses into the heap will be through the stack, right. And so in the course of execution of some program which deals with a large amount of dynamic data and which continuously keeps allocating fresh space and deleting old space, what can happen is that the heap can get fragmented. And when the heap gets fragmented, what it means is that you might have enough space all told to allocate a fresh structure in the heap, but that space might be such that it cannot be allocated contiguously. So supposing you have a large record which requires I do not know 10,000 bytes and you are going to allocate it in the heap, there might be all told 10,000 places available in the heap, but they might all be so fragmented that you cannot change the structure of the record, because once a record structure has been fixed at compile time, usually what it means is that you have to allocate that much of contiguous memory also at runtime in order to be able to access the record components. So what is frequently done is that the heap space is constantly coalesced so as to make it less fragmented. So if you open the Emacs editor, for example, which is based on Lisp, and languages like Lisp believe much more in allocating space in the heap than in the stack, because all lists that are created are dynamically created, right. So, as a result what happens is that this fragmentation is periodically removed by moving data so that they form continuous chunks in the heap, okay. And thereby what that also means is that if you are moving data, you cannot move data, which means the base addresses in the stack also have to be modified, right. So, in order to prevent fragmentation, periodically what happens is that, or concurrently, while your while the program execution is being delayed for some reason, maybe in IO or that it's just waiting for some response from the user. At such cases what happens is that they often have an automatic garbage collector which does a compaction of the heap and gets it less fragmented. So, what it means is moving a lot of data around and moving a lot of pointers around. And the actual algorithms for doing garbage collection are something that you must have learnt in your data structures course. I mean, there are the standard reference count methods and the shore weight mark and sweep algorithm, which are used for first marking. What you have to know is what are valid data items in the heap and what are not data items being used anymore. So, what you have to do is for each data item you have to know whether there is a pointer in the environment, in the current environment, which actually points to that data item. If there is absolutely no pointer, then what it means is that that portion is garbage and can be collected, or some other data can be moved into that, right. So, a heap is subject to a lot of variation which is unknown, which is not really visible to the user unless some explicit message comes. I mean, very often the compaction of the heap is visible to the user in some particular way. It usually gives you a response like please wait, garbage collection on, or some such thing, and this is something that our Emacs editor on the Himalaya constantly does. The amazing thing about it is that it does garbage collection even before you started the editor. So, but that's something that is it's just that it periodically runs the garbage collector even if there is no garbage to be collected, right. So, that is perfectly okay. So, if you let us look at the runtime stack, that is the only thing that is really accessible. So, that contains a current environment pointer. So, this current environment pointer is usually stored in some register. It's a base address of the current activation record, and your actual code that is generated will reside in some other area of memory, and there is a current instruction pointer also stored in a register. This current instruction pointer is really the same as a program counter, right. And so, this current instruction pointer is usually in a high speed register and it points to the next instruction that is to be executed, right. In many cases what can happen is that not all the data might be stored in the stack or the heap. Certain data which are compile time evaluatable like constants are often stored along with the code segment, because we will look at it, but very often if it is compile time evaluatable in a particular language, then what it means is that you can save on execution time by pre-computing the data values, and at compile time of course you have no absolute addresses or you have no stack space, you have no idea how the runtime stack is going to look. So, what you do is you allocate those constants immediately below the code segment. I mean, this is standard practice. I mean, most assembly languages have an allocation for data immediately after their code. So, similarly the constants would be stored in some area just immediately after the code for a particular block, right. So, this is a sort of typical structure that most languages with block structure would satisfy. Yeah, most their implementations would satisfy this sort of constraint. Yeah. So, let us look at some certain issues. Firstly, when you are looking at block structured languages, there are and their implementation, we have to distinguish between two things. One is the scope of an identifier and the other is its extent. So, if you take a typical Pascal like language, if you take our while language which allows declarations in blocks, here you have a huge while loop with a block being the body of the while loop, and this block of course contains a declaration D1 followed by some code C11, and this is followed by another unnamed block with declaration D2 and a code C12, and at the end of this there is another piece of another command C13. So, this all these commands could be compound commands. So, when you look at so if you look at the declarations in D2, so they have a scope that spans just this block, and if you have look at the declarations of D1, it has a scope that spans this block, and of course this is part of some larger program presumably. So, there is a global there is something that is global also, right. So, scope really refers to the program text over which declarations are usable, right. So, what we are looking at are is the notion of static scope. This example shows you what static scope is about, and this static scoping is what is followed in most languages like Pascal, Scheme, Algol 60, Ada, ML, Camel. So, the whole idea is that you can look at the program text, that means you take a printout of the program and you can clearly identify what is the scope of each identifier. And the most standard static scoping structure is that any reference to an identifier is refers to a binding created by the innermost enclosing block in which there is a binding for that in which there is a binding occurrence of that identifier. However, the important thing is that this static scoping I mean static scoping is not the mechanism followed in many languages like Lisp, APL, Snowball. So, in fact, Lisp though is very close to Scheme, there is one important difference that in Lisp everything, all scoping is what is known as dynamically, it follows a dynamic scoping as part of the language definition, whereas Scheme is statically scoped. What that means at this point, before I go into dynamic scoping at this point, but what it means at this point is that given a printout of a Lisp program and given an arbitrary reference to an identifier in that program text, there are no sure guarantees as to where is the binding for that identifier. Okay, I mean what I mean is it's not possible to infer directly from that text where the binding occurrence for that identifier is. What in particular in languages like Lisp, APL and Snowball, the binding is dependent upon the calling structure. So, it really depends upon the runtime structure, and it is not its execution determined, and it is not determined by a purely textual manner, right. So, that is in fact an important difference between Scheme and Lisp, even though they are otherwise almost identical. Yeah. So, static scoping makes for one thing it makes program readability easy, because you can determine the scopes of all identifiers in the program. You can by allowing by using a static scoping method, what it means is that bindings are found as close as possible to where they should occur rather than elsewhere, whereas in languages like Lisp, scoping is really runtime dependent and not and not text dependent, right. Okay, so that is as far as scope is concerned. But a related issue is that of extent of an identifier or the lifetime of an identifier, right. So, if you were to so 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 to put things more formally, let me just, static scope just means that it refers to that part of a program text in which all applied occurrences of an identifier refer to the same binding occurrence of the identifier. Yeah. So, given an arbitrary identifier, given an applied occurrence of an identifier, you want to know which is the binding occurrence, and it refers to that part of the program text in which all applied occurrences of this identifier refer to the same binding. Yeah. So, the other concept that we have to look at is the notion of extent or lifetime. So, an identifier, right. So, if you were to take this typical program that we have got here, yeah.
The binding remains the same throughout the program.
No. This Pascal is a typically static scope language, statically scoped language. What it means is that at compile time, whenever we say static or dynamic, we mean at compile time or at runtime. In the case of interpreted languages, this which are not compiled, you would say translation time. So, the most general term would be to say translation time rather than runtime, rather than compile time, right. So, we are, by scope, we are just looking at, we are saying that this is a region of the program text as it is written, as it is actually written by hand, if you like. So, we are talking about this region in the program text. That means, for the declarations in D1, I am talking of all the text that appears between this left braces and this closing right braces. That is all. I mean, it's a purely textual matter. Okay, but the fact that it is purely textual also means that it is translation time. It is only translation time dependent. What is the binding corresponding to an applied occurrence of an identifier? Dynamic scoping means that it is not, it means that it is not something that you can determine at translation time. It is something, given an arbitrary applied occurrence of an identifier, it is only at runtime that you can determine what is the corresponding binding occurrence of that identifier. So, that is what dynamic scoping means. Yeah. So, whereas static scoping means you can see at translation time itself, you can determine at translation time itself for a given applied occurrence of an identifier what is its binding occurrence. And if you can do it at translation time, what it also means is that I can read that program text sitting in my office without a terminal and determine exactly the scopes of all identifiers. Yeah. Whereas in a dynamically scoped language, or in a program written in a dynamically scoped language, I cannot sit away from the runtime environment and determine what are the binding occurrences of arbitrary applied occurrences of identifiers. Yeah, right. So, so let us look at this program. So what we would like to look, so I have chosen a while loop for a very specific reason, because that illustrates the difference between scope and a related concept, which is extent. So, scope, at least in statically scoped languages, refers to something that is compile time determinable or translation time determinable, whereas lifetime actually refers to, or its extent refers to the various the duration during runtime when that binding occurrence is applicable. Okay. So, if you look at the execution of this program, if you look at the typical runtime stack for the execution of this program, then what happens is that you initially you have an initial global environment on the runtime stack, okay, and as you get into the while loop, you are entering a new block. So, now a new environment rho 1 is created by the declaration D1, okay. So, which means all the variables that are declared in D1 have a lifetime starting now at this point. The moment this new environment has been created, those variables which have been declared in D1 begin to they are born at this point. Now, you enter the next nested block, you create a new environment rho 2, okay, and so the environment, so this, as long as this environment rho 1 is present, those variables in the declaration D1 continue to have their extent at this point, and at this point the variables in the declaration D2 are born, okay. Now, when you exit the innermost block, after you have exited C12, this environment rho 2 is lost, and therefore, all the variables that were declared in the declaration D2 are lost. So, the variables in D2 have a lifetime that spans only from the moment control enters the block D2 semicolon C12 and you execute C12. Throughout the execution of C12, these variables are alive, so to speak, and they die as soon as you exit C12. So, when you are entering C13, which is back to the original environment consisting of just this, these variables are no longer alive, so they are dead, okay. And now, after you have exited C13, I mean it's since it's a while loop, what could happen is that you get back into the original environment. Now, those variables that were declared in D1 have a lifetime spanning from this to this, okay. So, when I am talking about variables, I am talking about identifiers which are bound to locations. This location, the locations on the of the variables in D1 are available only up to this point, entering the body of the while loop and exiting that last portion C13, right. Now, what happens is when you re-enter, when you get back again into the body of the while loop, again the environment rho 1 is created, okay, but and so these variables in D1 are again born, but what I mean, and so through the next iteration they have this lifetime, but these are not the same as this, right. So, the extent is a runtime concept, and remember that our semantics always says that you should make a new location available to you. So, theoretically at runtime these storage locations need not necessarily be the same, it is just pragmatic that you might be reusing the same storage locations. Otherwise, think of it as follows: if the variables in D1 here had a lifetime which spanned up to here, then the original values that the variables contained at the end of this execution should also be available here, but they do not, right. They are freshly reinitialized, they have the same names, but since you can execute that portions, so they have several lifetimes. So, there is so theoretically speaking, this is one lifetime of this variables, this is another lifetime of those variables, and there is no relationship between these two lifetimes, except that they come from a common scope. They come from, they have similar, they have the same names, except for that there is really no connection between these two lifetimes, right. So, when we are talking about an extent or a lifetime, it really refers to the time during execution in which all applied occurrences of an identifier refer to the same storage location that is bound to the identifier. And in different lifetimes you have different storage locations, at least theoretically. It's if I had disposable memory, as soon as I have used it once, I just throw it away and I get new memory. I mean, it's equivalent to that. It's just that we can't afford disposable memory. But essentially a lifetime really refers to that span in the execution of that user program when an identifier location binding is created and that identifier binding is the identifier location binding is destroyed. The identifier binding location might be created again, but then that's supposed to be a different location, because there is no continuity between those two lifetimes. It's supposed to be a brand new location. Yeah. So the extent or the lifetime refers only to the time during execution in which these applied occurrences of an identifier refer to the same storage location binding to that identifier, right. It is important to distinguish between these two, because there are, for example, the global variables of a Pascal program have a lifetime that spans the entire program execution. Okay. There are languages, so in most languages, at least the statically scoped languages, you would have either blocks. Algol 60 has I mean, the notion of blocks that I have defined in my language really comes, or the notion of unnamed blocks which have declarations and commands really comes from the Algol 60 unnamed blocks, anonymous blocks. Okay. In Pascal, for example, the notion of a block is just a procedure or a function. Okay. In Ada, of course, they carry things further. You might have packages, you might have tasks. I mean, these packages are really modules, tasks are for concurrent or parallel execution of programs and so on. So, the basic notion of a block in these languages, and which therefore determines the notion of scope in all statically scoped languages like this, is whatever. So, the scope is basically a block. What the notion of the block is might vary from language to language. In the case of Algol 60, you have both the notion of unnamed blocks, procedures, functions. In the case of Ada, you have procedures, functions, packages, tasks and unnamed blocks. In the case of Pascal, you have just procedures and functions. Okay. And the extent is just the notion of extent comes from the fact that you are dynamically allocating, at runtime you are allocating storage to the identifiers or to the variables in a block. So it is from, so the extent or the lifetime is just from the moment of entry into a block to the exit from the block during execution time. Yeah. And if you enter and exit the block several times, then then they are all different lifetimes, and no two lifetimes have any relationship with each other. For the same identifier, no two lifetimes have any relationship, right, and that is because of your dynamic allocation. There are lots of languages which actually do not distinguish between scope and extent too much. Okay. So, for example, if you were to take languages like Fortran and COBOL, the notion of scope is just whatever is the notion of a block, which are just functions and subroutines. I mean, subroutines are like Pascal procedures. Okay, they change the state, and the extent is such that it is the duration of the entire execution of the program. So, regardless of the scope, regardless of in what scope an identifier has been declared, its extent lasts the entire program execution, and it is not just, I am not talking about just global variables, I am talking of even local variables. They have a lifetime from the start, from the moment of from the start of execution of the entire program to the end of its execution, regardless of whether you have entered a block or not. Every variable has a lifetime that spans the entire program execution time. Yeah, and this is due to the fact that in most language, in Fortran and COBOL, they actually allow a static allocation of storage, and it in fact follows a different runtime model, in the sense that you have data associated with every block, and all the blocks are allocated separately. There is no there are of course common areas, but let us not worry about that. The basic, a simple Fortran program which consists of functions and subroutines would be such that all the data that has been declared by the in that block is also allocated along with the code for that block. So what happens is that you can enter a subroutine, exit from that, enter it again, and the previous values will be preserved. So they have an extent which lasts the entire, which is different from the scope of. However, if you without entering a subroutine, you cannot access its local variables. So the scope rules disallow the accessing of variables that belong to a different scope. However, those variables carry their value throughout the execution of the program, regardless of whether you are inside that program or inside that block or not, right. So, and actually in some ways this is a very simplistic method of doing storage allocation. You just based on your compilation of the code, you just also directly allocate the storage that you require, and so you have the total amount of memory that is available to both code and the runtime structure is just divided up in terms of the blocks. This block requires so much memory, so allocate it that much, and so for each block you just allocate as much memory as it requires for both its code segment and its data segment at compile time. Okay. The result of is a static allocation of storage means that you cannot have dynamically created you cannot have any dynamic creation of data. Okay, which means there is no notion of a heap space in an implementation of Fortran or COBOL. There is absolutely no way you can do pointer arithmetic except through arrays, or you will have to, but then you are statically allocating all the heap space that you require within the data segment itself. So the only way you can build pointers and lists and so on is by allocating a huge block of storage, saying that I am going to program all these pointers and so on through arrays, that is it, and use only that area that is allocated to that data. So you have to pre-declare how much area you are likely to use in the heap, right. Most of us who are used to programming dynamic data structures in languages like Pascal really have no idea how much the heap can grow, or we do not care. But if you are going to do such things in Fortran or COBOL, it means you better know how much memory you are going to require and declare it. There is no alternative to that, because the entire amount of memory, so the maximal amount of memory that you will require at any instant during program execution would have to be declared in the program itself. so that it can be allocated at compile time, and at execution time there is no question of allocating memory. So, what it means is that having an extent that spans the entire program execution means that you are making suboptimal use of the memory. So, your scope rules do not, while you are in the main program, the scope rules do not allow you to access the data of a subroutine, but all that data is still there, right. So, you are making suboptimal use of memory maybe, but the result is that it's the Fortran programs execute among the fastest in the world, because there is this extra overhead of dynamically allocating memory is absent. The result of all this static allocation is also that you cannot nest structures in, you cannot nest blocks in Fortran or COBOL. All blocks will be kept separate. And since it is statically allocated, you cannot have any recursion, because when you are talking about recursion in invocation, recursive invocations, then you are dynamically allocating more and more activation blocks records for that, for a recursive invocation, and you do not know beforehand how many activations are going to be required for a condition to be satisfied and the recursion to terminate. So, you cannot have any recursion, you cannot have any nesting, but the executions are very fast. You have to determine the amount of memory you require initially, and but you are guaranteed very fast production style executions. On the other hand, what it means is that in the case of these statically scoped languages, you are creating a fresh activation record at each time you enter a block, and you are deallocating that much of storage each time you exit a block, right. So, if you are going to do that, there are the overheads of actually doing this allocation, because the allocation has to be done. I mean, you have to do a lot of bookkeeping, and what you have only is a certain amount. You are optimally using memory maybe at given program, I mean at any instant of the program execution you are using exactly as much memory as you really require, but what you are doing is you are doing a lot more hard work in doing the allocation, initializing, storing and so on and so forth, and consequently you are going to get slower executions, but it allows for a nesting of blocks, it allows for a natural development of the program in a stepwise refinement fashion. It allows you to make clear what is going to be local to a block. And it allows recursion, which is a very powerful mechanism for most people who cannot analyze recursion enough to convert it into iteration. I mean, it is a very simple way of a large number of mathematical problems are recursively defined. So, it is very simple to just encode that recursion in your program. Whereas, if you were to write a Fortran program, you would have to completely analyze that recursion and transform it into a pure form of iteration, and also calculate exactly how much storage you require before you actually write the program, right. So, these powerful, because of these powerful methods of program development which are available with a dynamic allocation, what it also means is that your executions are going to be slower, because of this extra overhead of having to do an allocation of memory each time a block is entered, right. Right. There are of course very often in the original definition of the Algol 60 language, people thought that this people I mean the designers of Algol 60 came up with the static allocation strategy initially. I mean came up with the dynamic allocation strategy, and the whole runtime stack structure and so on came up with Algol 60. But because of the fact that these extents were finite and did not last the entire program execution, it was felt that if you are going to allocate and deallocate at every time at entry and exit, how are you going to program something like a random number generator which might be used by your program, but is not part of it. It is not really part of it. You are just taking a random number from a random number generator and you are using it. So, you do not want any part of that code of the random number generator to be mixed up in your program, especially if that random number generator is going to be something that everybody is going to use for simulation purposes. So, I do not want to declare global variables, especially for example, the seed of the random number generator. After having generated some random numbers, to generate the next, and of course these random number generators are all pseudo random number generators. So, if you start again, I mean if you keep allocating and deallocating, each time at entry you will generate the same sequence of random numbers, right. So, the random number sequence at different lifetimes are going to be the same, and you do not want that. I mean if you want a true simulation behavior, you would like the last random number that you generated in the last lifetime to be somehow preserved, but you do not want that to be a global part of your global environment, because you are using only the random number generator, and yet it has to be preserved. So, so what they did was they allowed certain variables to be declared locally as own. Remember that the random number generator might be written by somebody else and you are just using that. So, that in that code some certain variables are declared as being statically allocated. Okay. So, they thought that that would solve the problem. It is an ad hoc solution, and in fact this ad hoc solution has been institutionalized in C. I mean there are these declarations called static which explicitly tell you that these things have to be allocated not at runtime, but at compile time itself, and that they should have even though they have a scope which is local, they should have an extent which lasts the entire life of the program, right. So, but most other languages have similar means for looking at scope and extents and so on, but these are the broad classifications. I mean there are parts of Fortran which allow for sharing of memory. In those days memory was very scarce. I mean you had only 32K for the entire computer system with 200 users. So, I mean memory was really at a premium. So, you had to allow sharing for memory. So, each user got very little memory. So, you had to allow sharing in the sense that between different routines, between different blocks, you allowed different names to be allocated the same area of memory, and that area anyway had an extent that lasted the entire program's execution, which means that there was an aliasing problem. There were different identifiers referring to the same location, and if an identifier was not initialized, and Fortran had a default initialization for integers and reals that if it is not explicitly initialized then it is 0, but if it has an extent that spans the entire program execution, then if you didn't have a if you had default initialization, what it means is that your program could often work wrong, because as a programmer you assume that it would take a default initialization, but since it has an extent that lasts the entire program execution, the initialization was in fact the last value, the last exit from the block, right. So, it led to a lot of insecurities in the language. So we will continue with this pragmatics next time.